All right, Vanessa, are you good to go?
Yeah.
All right, so welcome to our seminar, second distinguished speaker seminar. It's going to be on deep learning for multi-well automatic log correction, and it's given by Vanessa Simoes. Thanks for being willing to share with us about your work and for your time. Vanessa leads log quality control and improvement projects in the digital subsurface intelligence teams in SLB Houston. She graduated in computing and applied mathematics from USP in 2006. She received her master's degree in mathematical modeling and her PhD degree in mathematics from the IMPA in 2009 and 2013, and concluded two specialization programs in data analytics and deep learning at PUC Rio de Janeiro 2018. And she joined Schlumberger in 2013 and has worked as a research scientist and data scientist in Rio de Janeiro, Boston, and Houston. Her technical interests include renewable energies, acoustics, data analytics, statistics, and rock physics. And with that, I'd like to hand it over to you, Vanessa. The floor is yours. Thank you.
Thank you. Thanks a lot for the invitation. And it's an honor to present to UT Austin. And thanks for the introduction. As you mentioned, I will present the work for automatic log correction. And the presentation will contain a brief introduction for the problem and the motivation for working in this challenge, a description of the methodology used, how we build and train our deep learning method, and field applications in two different formations, one in a subset of Bakken formation, and a second application in the Groningen field. And those applications increase by level of difficulty along the presentation. So we start with a very simple application of correcting only one log using synthetic alterations, and conclude with alteration of multiple logs and field noise, and the conclusion and summary. So when I joined the group, the subsurface team in Houston, I had the challenge of working in log quality control. And the main project at the time was defining outliers in the logs, which is a non-supervised task. And we saw multiple challenges happening for the different ways to solve this task. One of the challenges was that sometimes the log contains useful information, even though the value for that depth is different from what we would expect. For example, you might have a shift on the neutron porosity, and when you predict that neutron, it is far from the logged data, but you still have all the formation properties and the trends from that log. You don't want to just delete it and lose information. So we saw that before doing outlier detection, we had to perform a log correction. So instead of starting from outlier detection, I started to build other steps in the log QC workflow. One was bringing the data to a uniform format. So with the correct and same units, good variable selection of the main curves in the data set, and a sampling rate control to keep the multiple wells with similar sampling rate. Then there were, as I mentioned before, some of the logs, they are not behaving as expected, but they still have a lot of information. But there are other cases where maybe the log has been synthetically inputted with the curve, or it is extremely outside of the range of expected values. For example, a negative compressional slowness, or a very small negative gamma ray. Those pieces, they might confuse your ML method or any interpretation that you do with the logs. So we saw the need of identifying those first outliers that we call synthetic intervals, and not including them in our analysis. And finally, the main topic of today, the log correction. So defining local corrections that need to be performed in a way to improve consistency on your field. So if you are reading the same formation in multiple wells with similar petrophysical properties, you want the gamma ray to be distributed around the same value and not have a shift maybe on the distribution. And finally, after doing this correction, then we can go to multiple downstream applications, maybe for defining outliers or predicting logs that have been missing entirely or in pieces, or directly for interpretation, depending on how much completeness you need from your data set. The current scenario that we have for data is that multiple clients are revisiting legacy data sets that have been acquired using multiple tools, and that sometimes where we only have the basic logs and not mud properties or tool properties to help on traditional corrections. And also some many companies are pursuing big data models, and these models are hungry for a lot of data. So they want sometimes perform log QC in thousands of wells, where you don't want to spend much time in each well. And we want then to improve the consistency of the measurements for those wells, and in a reduced time compared to performing a manual correction well by well. And okay, so on motivation for using new approaches or developing new approaches, I brought an example, a schematic example of the gamma ray distribution in 5 wells in the same field. In this field, I have only 2 formation types. One is more radioactive or shalier formation, where I have gamma ray as a normal distribution with average equal to 70 GAPI. And another formation here with these yellow dots, a cleaner formation associated with sand. and having a distribution of 30 with normal distribution with average 30 GAPI. And I have logged the wells in this along these intervals. So looking at well blue, I see that it's predominantly clean formation. So if from that distribution, I expect it to have a large bump around 30 GAPI and a small bump around 70 GAPI, while on that black well, I have the contrary. It's predominantly shalier, so the larger bump will be centered on 70. So schematically, with the proportions of those distributions associated with the length crossing the different formations, I have these 5 distributions for the 5 wells, color coded as this square bracket. And for in literature, we have multiple traditional methods to do the correction. One is looking at the percentiles 10 and 90 that here I plot in these crosses. So the blue crosses are associated with 90 percentile and 10 percentile. And I see that even though my logs are consistent for each formation, so the tool worked well, there was no no correction being needed for that for those logs. They are consistent, but still these percentiles are not aligned. And I could also use the percentile 5 and 95. I will show later how they look like. We could use only align the percentile 50, so the the average, and also align the peaks. And the last method is one that I don't align the peaks, but I use this peaks location for a first filter for looking at the wells that might require a large correction. So in this case, for example, the peaks for the first distribution are all aligned. The first peaks for the second distribution are all aligned. And this is an indication that no correction is needed. Nevertheless, when we look only at the maximum of the distribution of well in blue and black, we see that here is the maximum for that well, it's 70, while the maximum of this one is 30. If you only look at the maximum of distribution without analyzing the data, you might think that those wells are shifted or require shifting, which is not correct. So all the traditional methods would fail on this example, and ask for a correction that is not necessary. For example, percentile 10 and 90, aligning them, we have this behavior. So it's an extreme correction. This is the traditional equation that is used. It's just a linear transformation with a shift and scaling. And we see that visually it is not good, especially because of these extreme blue and black cases. We could get better results looking at percentiles 5 and 95. So the difference between those points is smaller compared to the 10 and 90. But still, when we realign those points using the same equation just with different reference, we see that on this extreme, the curves look aligned as well as on that extreme. And when we receive a data that have been automatically corrected previously, we often see this behavior that on the streams, the curves are aligned. But when we see the distribution here, there is clearly something off. And this is the challenge that we want to attack with our methodology. We are not looking at the distributions for performing the correction. Instead, we are looking at the local behavior of the log. So the deep learning method is able to understand the niche formation we are and predict the necessary alteration to improve the consistent with the training wells. So the methodology works based on the convolutional neural network method that is built as an encoder-decoder. And for inputs of this method, we use noise and samples that we have altered using a combination of alterations. And as output for the method, I have the original samples. So I assume that the training wells have relatively good quality compared to my input samples. And the method then learns to receive this noisy data and predict a better quality output. So to train my neural net, I reduce the loss given by the difference between the original logs and the output logs. And for creating those samples, I make a combination of multiple alterations such as shifts in intensity, scaling, small depth shifts, small random noises, and deletion of one or more log types at a time. So I delete an interval and I force the method to learn what interdependency those logs have that allow the method to predict the output. So explaining visually, the strategy reminds of computer vision techniques. So from my input logs, I create windows that will be my samples. And for each of these windows, I use those logs as output, and as input, I make one or more alterations. For example, here, I deleted one log. Here, I shifted the gamma ray, and I can alter multiple logs at a time. Depending on the alterations that I make at this, in this training strategy, defines what type of tasks the method will be able to perform. So for examples, I brought an application on the backend data set. This field application is performed in 20 wells that have just one second. 20 wells that have been cleaned and edited by domain experts before I received them. So it's high quality logs. And I divide those logs into 15 train, 2 validation wells, and 3 test wells. This is a simpler case for selecting the training wells because all the wells had good quality. I could select randomly. And also for my validation wells, which is gives me a critical information during training to see if my method is learning with as the epochs evolve. I also I could select randomly. And the test wells, you will see it as colorful lines and points in the cross plots and the histograms are the ones that have been altered, and they have not been seen during the train and validation process. So it's new wells that have been hidden during the training stage. For that application, I have 3 cases. One, correcting only the gamma ray log, which is the simpler case. So all the other logs have good quality. Only gamma ray is altered. And case 2, gamma ray and N5 are altered according to those shifts and scaling. And both case 1 and 2 have are using the same deep learning method. And I don't tell the method which log has been altered. I expect it to identify and automatically correct. And there is a third case that is from the latest development, where I have alteration in gamma ray, HOBI, and N5 simultaneously. And for that case, it required me to train a more complex model that can solve both case 1, 2, and 3. So the field, the original logs are here in the left, and I see that the distribution of the logs are relatively similar, and I assume that all of them are consistent. I get the 3 test wells and add the synthetic alterations, letting them, and after the alteration, they look like well A, B, and D here. And again, those wells are separated from my train and dev set. So on the application 1, this is the only log that required correction. And before the correction, this is the distribution. So I see that they are different between themselves and also different from the training wells. After I apply the correction, I see a larger similarity between these 3 wells. In a depth by depth plot, I have the original log in red and the altered log using synthetic alteration in green. I see that the shift is not constant. There is also a scaling factor being used. And after the correction, there is a larger similarity with the original curves. One issue still to be improved on the method is that the ML output is moved compared to the input logs. And but the trend and the mean is well predicted. So for the case 2, I have alterations on gamma ray, so new alterations here, and also alterations on N5. I kept two wells with smaller alterations and one with intense alterations to see how the method behaved in these different scenarios. And I also kept well unaltered to see how the method behaved if it was causing a shift that didn't exist. And so the impact of the method on quantitatively, we see that the mean absolute error for the gamma ray is reduced when by using the log correction. So in yellow, I see the before applying log correction. So the log plus synthetic alteration has this mean absolute error in gamma ray. And after applying the correction, the mean absolute error reduced to less than 10 GAPI, even on the case of intense alterations. So the method was able to perform well, even in the case of that large shift. For N5, similarly, we see a reduction in mean absolute error for the 3 wells. So even on the case where there is this shift of more than 0.25 VV. And in the end, it was less than 0.03 and similar to the 2 uncertainty. So the method greatly reduced the error on gamma ray and N5 simultaneously. In a depth-by-depth plot, we see a similar behavior as the correction for gamma ray. So in the original logs are in red, the altered logs are in green, and the ML corrected is in blue. So I see that the method provided an output that is more similar to the input original logs than the input, and that it has a correct trend even on the case with very large alterations on N5 and on gamma ray, and certainly N5. And if we performed an outlier detection in this scenario, we would likely cut parts of this gamma ray. And if we apply this correction before, then we avoid this wrong flagging of logs just because it was not corrected. This is another scenario. So we have alterations on gamma ray and phi. And I also, in this case, it is the new model that is predicting the 3 outputs, gamma ray, neutron, and density. And I might or might not have alteration on density. And so in this case is only containing alterations in gamma ray and N5, very large alterations for N5 and no alterations in gamma ray. We see that the method correctly predicted a density very close to the input logs with the correct sharp alterations here for this zone and this zone. And it's a little smoother than the input, but with the correct trend, similar to all the logs. And on this case, I have small alterations on gamma ray and N5 and some alterations on density. In this case, it is localized alterations on density. And the method was able to clean these sharp peaks and predict one log that was similar to the original logs that I assumed to be the ground truth because they had good quality. So I see here the shape is much similar to the blue than the input log in green. And another test is giving the original logs as input. I see that for most steps, it is very similar to the input. There is only some alteration here on that zone. But when we look closely, we see that there was a shift on the input logs. That's why there is this difference for the outputs. As a result, the output are more aligned than the input logs. And we have seen this in multiple applications, but it only works for very small depth shift. It is not a method to performing this regular large shifts, depth shifts that might occur. So only small alterations such as that, and also because there was this large contrast that allowed the method to perform the correction. And the second application is for Groningen field. This is a more challenging scenario because the wells contain original field noise. In this case, I have 86 wells and they have with this complete set of gamma ray, density, neutron, resistivity, and compressional. And for making the selections of train and validation wells, I looked at zones where I knew the behavior. We have here a large zone containing anhydrite and malite layers. And I use this as these zones to both select the wells that required a large correction and separated them as test, and also to evaluate the method because I knew that gamma ray and N5 should be aligned in those intervals. And the application here is first correcting gamma ray and N5. And for building the deep learning method, I need training wells that are high in consistency. So I selected anhydrite and alite intervals for a selection of those wells. And these layers were identified by a simple rule on the logs. And so here are some examples of anhydrite and alite here. And so those wells had high similarity. The wells with high dissimilarity are presented in these slides. So for anhydrite zones, I see that the distribution is all over the place, and the same for alite. So the behavior here has a larger dissimilarities. It is there. It requires some correction for improving the consistency. And so similar to what I showed on backend, in here I have the inputs for anhydride zones. So I use this, so I train my deep learning method. I use this as input to the method, and then the gamma ray distribution that is predicted has this behavior. It is more similar to the train wells. I see that there are some peaks that are more concentrated than before, but it's impacted partially because of this moving effect that I have on this ML, and partially comes from the concentration on the original logs. Similar here for light zones. Here was the distribution before ML correction. Here it's the distribution after. So I see an increase with similarity with the train wells. Now there is some trend for the logs, and yeah, that's it. And when we look for the 3 test wells compared with the train well, we see the original distribution here. So there is a shift. This is on anhydride zones. And after the distribution, as I said, the amplitude is not the same. So the tails are different, but the zone with higher values, more likely values, are similar. And also when we look at the dissimilarity, the original logs had a high dissimilarity. When we look here, train wells versus the test wells, we have values of 0.5 or larger. And after the correction, it reduced to around 0.3. And the dissimilarity between the train wells also reduced. The test wells also reduced. And this is the original logs in red versus ML predicted in blue. Again, the correction is performed only when it is necessary, and it can vary with depth. In this case, I saw the gamma ray correction decreasing as you go deeper on the well. In that case, I see a sharp alteration here on the correction on neutron porosity, where I have an alteration also on the caliper log, and maybe because of different formation types. And I didn't force the correction to be constant. So as you can see, it might have some alteration with depth. This is a good, an advantage of this methodology. Usually if you perform the automatic correction using the linear equation that I showed, you have to define the zones where it's going to be applied, and it will be the same correction for the entire interval. And this might be time intensive to define those zones. And in this methodology, we don't use that. And this is another well where I have a light anhydride and the shalier interval on top of the reservoir. I see that the correction on N5 is almost constant along the interval, while there is some alteration on gamma ray. And yeah, but yeah, there is an alteration, but is consistently in the top part of the interval. And the second case that I mentioned, it's more challenging because it also allows for alteration on the density. And in this case, I'm using original logs, so I don't know the ground truth. It is only for by visual inspection that we can evaluate the method. And here we have the results from the method that I have trained in the last months. So it was after SPWLA. Instead of only having the shifts and scalings and depth shifts, I also allow it for more alteration, localized alteration in the logs. And I see that it was able to detect some peaks on the density that occurred naturally, and it predicted a log that is smoother than the original in those zones. One thing that is also nice, it is that it didn't correct this alteration on possibly coal layers that happen in this field. So it was able to get a sharp behavior here, and probably because these layers happen in multiple wells and it's consistent in all the logs. So it learned that this is a real possibility, even though there is a contrast, that it is consistently appearing, so it was not erased. And I performed a similar application for compressional, and I am applying in multiple fields. And in compressional, there might be cycle skipping or some mislabeling of arrivals that some peaks might occur, and also some entire intervals being following another mode. So instead of compressional, the interpreter might have selected the slowness from the shear for a certain interval. So I want the method to be able to correct in that case. And so I'd like to first thanks again for the possibility of presenting at UT Austin, and thank SLB for allowing to develop this research and presenting outside, and also NAM and Utrecht University for providing the data from the Groningen. This is a big petrel project containing seismic and logs and well tops, and it is available online. In case you want only the logs, I can share this information, or if you want the entire data set, if you look for these keywords here, you can find online. And so in summary, we have built a deep learning method for performing automatic corrections in a certain basic type of logs. And it has successfully removed systematic noise in field and synthetic noise. The impact is reducing the pre-processing time and increase data consistency. And ongoing and next challenge is increasing the range of applications to other logs and other alterations. The model only learns corrections that are similar to what we used on the training strategy. So it is important to understand how to model those alterations to teach the method. And yeah, so thanks everyone.
Thanks, Vanessa. Excellent talk, and we're open for questions.
Yeah, go on. Hi, Vanessa. Can you hear me?
Yeah.
Thanks a lot for the talk. Very good talk. I have a question. When you correct for the noise and you are harmonizing the logs for a specific depth, that depth is going to be like a physically representative depth or more like an average depth?
I didn't understand the depth being representative or alias.
I mean, for a specific point, you are going to perform a correction.
Yeah.
So let's say like the real value of gamma ray for a specific formation is 0. But during your training data, you have different values other than 0. So what is the likelihood that actually I'm going to be able to predict that 0 value?
Yeah, so it will only improve consistency. If the training wells, for example, in this formation of 0, but the ground truth for that formation type is 0, but my train wells are in average giving me 10 GAPI. So after correction, I will probably go to 10. It doesn't know the ground truth. Yeah. Does it respond?
Yeah.
Yeah, so that is why selecting those training wells is an important task. In the way that I did the selection on the Groningen is selecting a subset that had similar values for those anhydrite and alite layers. But I saw that the average was shifted compared to the tables that I have for those minerals. Yeah, so a small shift, not much, a couple GAPI difference, but it's still, I knew that my prediction would also have that behavior. Yeah. Same for neutron porosity. Yeah. Ideally, and that is I think a hard scenario to get, is having training wells that have been corrected, and then the model will learn on high quality data. Yeah, but for me, in my case, I'm finding it difficult. Usually I will only select the ones containing high similarity. Yeah.
So if I include like synthetic data,
yeah.
on-cam truth, can I generate that bias to make it more precise?
Yeah, building this synthetic data set is a challenge. But yes, you can certainly do that. If you have, for example, a formation and then you populate that log values, then it is, yeah, probably going to improve the results. One challenge on building the synthetic for this model is that it's a window-based model. It's not a depth by depth. So you want your logs to be representative. Does it make sense?
Yeah, they are make sense like in terms of the structure, you mean?
Yeah, exactly. Yeah. like the certain behaviors on the beds, because yeah, there are some complexities, yeah, on the logs, yeah.
Oh, based on that, it means that if I have, let's say, a river environment, when I have a thickening layer,
Mm.
do you think it's going to be able to recognize that structure and accordingly to that, or it's going to have any issues because I mean layers are going to have different structure and different points and probably different composition.
Mm.
of the other.
I think it, no, so I think it recognizes this challenge. Another challenge that it uh, is, I am seeing problems is, for example, when you have an alteration on the formation properties, maybe for change on the fluid that don't impact multiple logs at the same time, and it's not a common fluid in the reservoir. So I see a correction that should not occur. Yeah.
So it means that if I'm analyzing gas saturated formation, it's highly likely that I'm going to wipe out the gas.
And if there are only small pieces of gas, it might correct, predict a shift on the N5 that doesn't exist. Yeah.
Okay.
Yeah, it is. Yeah, I think this is the one in this recognizing complexities. This is the one that is challenging me. Yeah.
Any other questions?
No, that's right.
Yeah, okay, sure.
Last question is, do you think that you would be able to extract phases from
Yeah.
that analysis?
Yeah. So I use the same method. So in this case, I only showed correction, but I also use the same method for phases, for predicting logs. So it can extract other information than the original input. Yeah. Because in to solve the problems that I'm asking it to do, it needs to understand the intercorrelation of the logs. And yeah, so it will be only one output more, yeah, for the method. Yeah. Does it reply?
Yeah, yeah. Thank you.
Yeah, so I've applied it for finding certain lithologies, for example, the gas or the coal layers, when they were not frequent in my reservoir. I wanted to get a fast way to identify them and check if the method was, how the method was behaving. And it gave high accuracy even with a few positive examples in the training set. Even with a couple wells, I could train it. Also, I use that to predict zonations in a field, and it also provided a good quality prediction.
Great.
Yeah.
Thank you.
Thanks for all the questions. Yeah.
And we have time for another question. 1 minute. All right, thanks again, Vanessa.
Thank you. Thank you very much.
Let me stop the recording.